So going back to this idea that there's energy that hits the earth, right, from the sun. I showed you last week that electromagnetic spectrum. The energy that moves through space is radiation. It moves as an electromagnetic wave. That's the only way that it can propagate itself through a vacuum. Now, once it hits our atmosphere, it has some options. We have conduction. Conduction is where we have warm air that touches the ground, or the warm ground heats up the cold air touching it. That's how we get things like thermal inversions. But convection is the main process that happens in our daily weather. We know that air is a fluid, so it's able to move. It happens in our oceans. It happens in our tectonic plates, the magma in the mantle. So hot rises, cool sinks, and that is how energy gets moved from one place to another. We're basically our own natural thermostat. Why do some places absorb differently than others? This is a concept called albedo. Albedo is another word for the reflectivity of a material. So obviously light-colored things, snow-covered mountains, reflect a lot more energy than a dark forest. And this ends up playing a huge role, as you'll see next week, in global warming. Think about our poles. We have an entire continent covered mostly by snow and ice. That plays a huge role in controlling the thermostat of the Earth. We're going to look at a positive feedback loop that occurs at the North Pole. What happens as this ice starts to disappear? Well, it's going to speed up global warming because we have less reflecting and more coming into the planet. So melting sea ice is a problem. And we call this the heat budget, and we are a very temperamental planet. Remember, we have what's called an ecological range of tolerance. If it gets too hot or too cold, we get uncomfortable, and then some species can't handle that at all, and they die out. So that's called the Goldilocks hypothesis, keeping things just right. So for many years of my life, people were arguing whether or not the planet was actually heating up. Was global warming occurring? And one of the biggest mistakes people often make is we'll have a rough winter and they'll say, see, there's no global warming. Well, remember that climate covers a 30-year span. When we have a rough winter, that's called weather, but it's 1 out of 30 years of data. When we look at the data from multiple sources, we see that they all come to the same conclusion. When we see the emergence of fossil fuels, the industrial revolutions, we see this take off. And you got to be wary of your scale, right? How hot is it actually getting? We're talking tenths of a degree. So it's not like we're jumping 8-9 degrees a year on average. The problem is the idea of a positive feedback loop, the runaway train. If there's no end in sight to what this pattern is doing, we have a problem with our heat budget. And that's where we're at. We know the Earth is getting warmer. The question then became, whose fault is it? Is it natural? Does the Earth just get hot and cold sometimes? Yes, it does. We know that. Is it supposed to be doing it right now? Actually, yes. We're in something called an interglacial period where the Earth naturally warms. Should it be happening this fast? That's where we hit a big problem. No, it's heating up faster than it's ever heated up before. And could there possibly be a human cause to this? I just pointed out the use of fossil fuels. Okay, if any of you have problems with flashing lights and things, you may not want to watch this. But what we're going to see here is from 1880 on, countries around the world, and for each year, whether they were average or whether their temperature rose or decreased. You can see in the late 1800s, we had back and forth between cold and hot. But when we get up to about 1980, you're going to see mostly orange and red, and it's not going to go away. Still going back and forth up to the 70s. And look at that orange and red start to appear. The trend is obvious. You can see it color coded. We're insanely warming up. The greenhouse effect is a good thing. It's the reason we have life on Earth. If we were not able to bounce heat around down in the troposphere, we would be an ice ball. Water vapor is a greenhouse gas. Think about a cloud. It can absorb or reflect energy. It's just drops of water. Because of its short residence time, the length of time that the water vapor is in the air, it's not a significant factor in global warming. The other major greenhouse gases that I had you look at already, we've already talked about carbon dioxide. Methane is more potent. Nitrous oxide, the one that comes from gasoline and mostly from our agriculture, from all of our fertilizers. And then we've got the HFCs, those coolants, those refrigerants that we use. Those are your main greenhouse gases outside of water. Now on that website I had you look at, it talked about GWP, the global warming potential. We use carbon dioxide as a reference point. If carbon dioxide is 1, how much worse is methane? Well, here you see about 25 times worse. How much worse is nitrous oxide? Wow, almost 300 times as bad or powerful at trapping energy. And then when we get into the fluorocarbons, those are the real bad guys. But I have some slightly good news for you. Which one of these do you think we have the most of in the atmosphere? The answer is carbon dioxide. But methane's a bit of a concern because we know there are huge quantities of it stored in the rocks and in the ground. And when we do things like mining or fracking, that's what we're releasing. We're actually leaking and releasing methane into the air. Carbon dioxide is number 1 by a lot. And the majority of it comes from our electricity power plants and our vehicles. That's what comes out of the tailpipe of every gasoline engine in the world. Every single day. What do you think this is? Other carbon dioxide. Any guesses? We can see a change in carbon dioxide based on something like deforestation. So the forest used to take carbon dioxide in, we cut down the forest, now it's not absorbing as much. That's a problem. You can see the GWP, the fluorocarbons, make up the smallest chunk. Let's look at carbon dioxide, since it's the problem. Let's focus on that one. Here it is historically. 1850s, we see that the United Kingdom was by far the leader in CO2 emissions. Think of the London fog, right? They're burning all that coal. The USA caught up by the 1900s. Not quite caught up, but in second place. We've still got Europe behind us. In 1912, we pass up the UK, but because our country is bigger and more spread out, we don't have the pollution problems until about the 1950s. You're going to see Soviet Union start to creep up here. They're in 5th right now. Right, they become, the United States is just increasing its lead all through the 60s, 70s. Now here comes the Clean Air Act. Do we slow down? Not really. If anything, we speed up population growth. And here comes the Soviet Union. Oil, oil, oil there. And look at China. Look how fast China's moving, right? And remember, we're way past that beginning part where it was small. There, China is going to pass us up. And that's their smog problem they have right now. We're not doing enough to slow this graph down in most places in the world. Here's the data. When we look at parts per million, if we measure CO2 in the air, it took about 5,000 years of Earth history to go from 270 to 280. And then the Industrial Revolution kicked in. 100 years, 40, 30, 23, 12. We are still increasing instead of decreasing or stabilizing. We're speeding up how much CO2 we pump into the air. How do we know that? We measure it. There's actually multiple places around the world, and we can take averages and graph them together, and it's kind of interesting if you're a data nerd. But the gold standard, the one that we mostly look at, is in Hawaii. It's actually a wonderful place to measure climate data because it's in the middle of the ocean and there's nothing around it. So we don't have to worry about pollution from somewhere else drifting in with the weather. And notice it's cyclical. Every single year, the CO2 goes up and down, but the general trend is up. This is called the Keeling curve. He was the doctor who discovered it. Why do you think it's cyclical? Why does it go up and down? There's two main reasons. Go ahead, Henry.
Do we use less energy in different times of the year?
Different seasons, we use different amounts of fossil fuels. Yep, absolutely. So we got to heat up our furnaces in the wintertime. What's another reason? Yeah.
Leaves on trees.
Trees. During the wintertime, they don't absorb nearly as much carbon dioxide. So that causes a change in atmospheric CO2. So every year, due to the seasons, we see a pretty big back and forth that occurs. All right, well, notice this goes back to like 1950. But the famous graph that kind of ignited this debate over climate change and human cause is this graph. This graph shows us the last 10,000 years. Ever since the last ice age, we were pretty stable, slowly warming up. And then boom, Industrial Revolution. We are doing this. We are at unprecedented heights. They call this the hockey stick graph because it's kind of shaped like a hockey stick. But it's the scary one. You should look at that and think, oh my gosh, that's not okay. And it's our fault. Okay, but what if we go back further? Because the Earth has always gotten hot and cold. That's what happens. Here it is again. We have 800,000 years of data. I'll tell you how we got that in just a second. We see that, yeah, it varies quite significantly up and down. But this is CO2. Does it match temperature data? Is CO2 a good measurement for variations in temperature? And the answer is, it's almost perfect. What you're looking at here is called an ice core sample. We can go down to Antarctica and drill down in the ice, and just like soil layers in the Grand Canyon, it's a history book. And trapped in that ice are gas pockets, little bubbles. And so they can actually withdraw the air from one of those bubbles and figure out how much CO2 is in the air. So we have 800,000 years of data because we have 800,000 years going backward in the ice cores. Once again, those are from Antarctica.